Okay, good morning, everyone, and welcome to this Capital Markets Day for Green Minerals, the first one in our history. Before we start here, Erik, I think you need to help me. Probably frozen. Yeah, here we go. Before we start, we got a brief disclaimer for anyone to read. Presentation is on our website. And before we get into the details here, I just want to provide a brief overview of the company as we are today. So Green Minerals is one out of two listed deep sea mining companies globally. The company is headquartered in Oslo. We are listed on the Oslo Stock Exchange with the ticker code GEM, which I think is very fitting, NO. The company sports a modest market cap of $8 million. We had some massive news for the company, for the industry, and indeed for the company on the 9th of January this year, when the Norwegian government or the Norwegian Parliament, I should say, opened up for deep sea mining. With this, Green Minerals is approaching our next phase, which is license ownership. Today, we are going to present targets for the company in the form of license, our first license win, which we expect to be the first half 2025. We expect our second license win to come in the second half of 2025. And there we have a MOU supporting that target. We expect to start production in 2028. And as we will see later on, the economics in this project are really attractive, and the company cash return on investment, which is different from project cash return, but company cash return on investment pre-tax looks set to go above 300% per year. The team presenting here today is as follows, led by Ståle Monstad, our CEO. Ståle has more than 25 years of experience in exploration in oil and gas, and comes to, or came, I should say, to Green Minerals from the position as a chief geologist with Aker BP and senior vice president of exploration of Aker Energy. Our chief engineer is Maxime Lesage. Maxime has worked more than 10 years on complex subsea construction projects, and also completed his PhD on deep sea mining production systems on the NCS. Espen Simonstad, Senior Advisor Geoscience, has more than 10 years experience from the oil and gas industry, and notably 8 years with the Oil Directorate, where license management and application processes were key tasks. And then Angela Makava is our ESG lead, and Angela has a background in international trade and supply chain management. And for myself, I'm the chairman of this company. I founded it 4 years ago under the umbrella of Seabird Exploration. My background is in the financial industry, investment banking, and as an investor. I've been the chairman here since founding the company. The ambition that Green Minerals launched when we started the company, and the ambition that we presented to our investors who were a part of that founding, was to become a license holder in one of the world's most attractive copper resources with the lowest use of capital possible. This has been a cornerstone of our ambition and our strategy all along, the lowest use of capital possible. Subsequently then, after winning a license, to deliver 1.5 million tons of world-class quality ore for offtake. And as I said, the strategy to get there is extensive use of partnerships, and therefore an asset-light strategy, which we think is key on a long-duration project like this. Status for the project as of now is, as I said, we had the opening decision on the 9th of January. Our production concept is in place, which we will go in detail into. We have proven blendability with terrestrial ore with our joint processing study. And on the 30th of April, Green Minerals was invited by Norwegian authorities to nominate acreage for licensing. Therefore, I'm really pleased to say that the company is en route to deliver on stated ambitions. We expect then to win our first license in the first half of 2025, first ore 2028, and as we will show, we believe we can deliver unmatched capital efficiency versus traditional onshore mining to our investors. When it comes to license work, we want to emphasize that despite the modest market cap of the company, Green Minerals actually holds $50 million worth of exploration data transferred to us from the Oil Directorate. This forms the basis for our exploration planning. We expect to file our first license application in the second half of 2024. So the next few months, this will go in. We already talked about the license award, and we believe the company, having prepared for this for the last 4 years, is in a very good position for a license win, and we are indeed ready to execute on any awards. And with this, I hand it over to Ståle Monstad, our CEO.
Thank you. Good morning, everyone. One of the the key things about this business is that the world really needs more metals in order to change out the existing energy system with an electric energy system. You need the materials to build that. And at the moment, there is no immediate solution in sight unless you actually start also utilizing ore from the sea. I like this picture because it illustrates one of the cables that goes from the offshore wind farms. And just to give you the right ideas in the head, that cable, each meter of that cable is 50 kilos of copper. And it's hundreds of kilometers with cables that are going to come from offshore wind farms. There is an enormous need for more copper for the grid, for just distributing electricity and bringing it to shore and so on. And we see it also on the table on the left-hand side, that offshore wind is really using a lot of metals in order to work. And if you compare that to what we use today as natural gas and coal, you see it's really a major difference. And of course, the other big thing is the transformation from a fossil-based car park for personal transport to electric cars, which also is a driver for this. So if you look at the key metals or minerals that we expect to find on the Norwegian sector, it's copper and it's cobalt. Cobalt is mainly for the battery, EV batteries. Copper is needed all over the place. And copper is the metals that really has the most absolute growth, with about 9 million tons if we are to reach this ambitions of net zero by 2050. knowing that, and knowing that the sort of copper ore onshore is on a quite a steep decline. All the easy copper, all the obvious places have been mined, and the ore grade. This is for Chile, the world's largest producer of copper. We see that it's just steadily dropping down, meaning that for each rock you sort of mine, it went from an average percentage of copper in that ore from in 2005 and 1.1%. It's now below 0.8. If you look at the Nordic countries, in Sweden they are operating on 0.17% copper in the ore. In Finland it's around 0.25. So the ore grade is really dropping down, and that has implications also for the energy cost of mining, of producing copper. If you want to produce a kilo of copper, it takes much more energy now to make that, to process that and go to the smelter, because the ore grade is so low. And also looking at the recycling rate of different metals. This is quite a busy table. I want to point out copper over here. Today we recycle almost 50% of all the copper that is produced, which is okay compared to many other metals. We can do better, but it will never be enough to sort of build all the new stuff we need to electrify the energy system. If we look at today's recycling, it is enough to cover 30% of the need today in 2024. But this was 2022, but still. And also we see that all the predictions said it's going to be a supply deficit in copper. And that is not because we are constructing or building more sort of what we used to build more or less forever. It is really to the grid, to largen the grid, and also transport for the EV. So copper is one of the elements, one of the metals that is most hard to replace with something else. You can't just change it out with something else because it has unique, it's a unique metal. So the mining companies saw this. It's going to be really interesting to find more copper. So from 2002 up until 2011, they increased the investments into exploration with 600%. So the money that went into looking for more copper increased 6 times. But the result was not very good. They didn't find much more copper. That has several reasons. I said all the easy copper has already been found and been mined. It's more difficult and it's more remote and challenging locations. And actually, since 2018, only one new copper discovery has been made on land, on shore, which is not going to be enough, obviously. And that is also seen that it's actually a shortage of copper ore now. This is the price for the smelter. It's actually negative at the moment because the smelters doesn't have enough copper ore to keep their plants running. So this is a graph from Bloomberg and CRU Group. And with this decline in ore grade, how much copper you have in the ore, also comes a rise in the sort of cost for producing each ton of copper. So we see in Chile, which again was the cheapest place to produce copper, they had most copper mines since 2006. It has gone up from $5,000 to more than $15,000 per ton copper in production cost. So the cost of producing copper on shore is also increasing because the ore grade is going down. And we have to dig deeper and deeper and deeper into the ground to find the metals we need. This is a graph going from 1950, where almost all of the mines were in the upper 100 meters. This is onshore. See how this is moving down. This graph shows down to 800-900 meters. And that means you have to dig out a lot of rock that is going to be waste before you actually reach the ore that you want to produce. So all these are signs that the copper we need for the electrification of the energy system is very difficult to get from onshore production, alone at least. We know, I'm a geologist, and I know that there's more than enough copper on continental crust in the world, but it's going to take a lot of nature and a lot of hard work to actually get that out, because the ore grade is so low. And just a statement here from BlackRock, which means that to incentivize for new investments into onshore copper ores, you're going to need a copper price of $12,000. And the price today is, I haven't checked today, but it's around 9.5, 10 in that region.
We're about 10,000.
10,000. And as a contrast, we foresee an average copper grade between 2 and 6% in SMS deposits, or a span of copper grades. And we are, of course, aiming for the highest ore grades, and we have used 5% copper in our economy. So we think if you look at the difference between 0.7 in Chile, 0.25 in Finland, when you start taking from 2, 3, 4, 5% copper, it's a big difference, and it means a lot less energy into the production of copper. Just a few words on the sort of geopolitics. There are 3 main blocks: the EU, the US, and China, and they all have made their sort of list of critical minerals. And in the area in the middle here, you see the elements that are common to all these different blocks. And both copper and cobalt is on all the different lists of critical minerals. It is really, I can't stress this enough, but copper is the key to electrification. Simple as that. On the flip side of that, the processing and mining is controlled by very few countries, which means that the supply chain is, at least, it's not very secure. We see that China is dominating processing for all the key elements that goes into this new green shift. And they also control a lot of these mines that are marked with Congo and Indonesia and so on. So China has a very strong grip on the mining sector, and particularly the processing part of it. And we have seen lately that China is using that monopoly or that power by starting with graphite, which is really important into batteries. They have restricted the export of graphite, making it a graphite squeeze, at least for if we are to realize all the gigafactories for batteries that we plan in the West. There's a recent publication from Rice University in Houston stating that China is also positioning itself to dominate the copper supply in the world. And I think a lot of the politicians in the Western world are a little bit scared of having China too dominant, also within copper. And as a result of that, more and more countries around the world are adopting their own mineral strategies. All the countries that have a sort of color, and that is not gray, have sort of adopted a strategy between 2010 and 2023. And Norway actually is gray here, but they adopted this mineral strategy published on June 21st last year. Just a few words on the process in Norway, where we are. So we have gone through a story, you went through part of this. The parliament vote in January, which was the first main hurdle. And now they have announced the nomination, and invited for that, there's going to be a public hearing on the nomination itself. And application is expected in Q3 or Q4 in this year, and award early next year. And the area that is where we are invited to nominate is reduced compared to the original assessment area by 2/3, roughly. So it's a little bit over 200,000 square kilometers. And the nomination deadline is actually in exactly 1 week. And we feel that we have a strong support from the Norwegian government. These are statements from the Oil and Energy Minister Terje Aasland, and also Prime Minister Jonas Gahr Støre, all seeing the importance of at least looking into the possibility of having the deep sea as a source for critical minerals. And we also have sort of a responsibility to look into that, because the world needs metals, more metals. The Norwegian used to be Petroleum Directorate, is Offshore Directorate now. They made a resource report, and that resource report concluded that the sort of potential in Norway is really a significant potential also on global scale. And we're going to look more into the exploration part of it with our senior advisor for geology, Espen Sinestad.
Thank you, Ståle. I'm going to talk you through the fun part, the exploration, the first part that we are looking into now. So, as Ståle mentioned, the area is now open. More than around 281,000 square kilometers open for mineral activity, with an 80-20 vote in favor at the Norwegian Storting in the Norwegian Parliament in 9th of January, and was formalized in King Council now a couple of weeks ago. We are one of the recognized industrial actors that have been invited to nominate acreage within this area, and the nomination deadline is, as mentioned, next week. First, initial de-risk have already been done by Norwegian authorities and academic institutions. Data covering all of this area in different kinds of bathymetry, geophysics, and so on, sampling, drilling, have been done by Norwegian Offshore Directorate, University of Bergen, Tromsø, etc. And the value of that, more than $50 million, have we now access to, and that's they have already done the initial risking or de-risking of the acreage we are looking at. So we're going to use that in our work on the nomination and also further into the application part. And as Ståle mentioned, as part of the impact assessment, the Norwegian authorities did a resource assessment. If you look at it on a graph like this, you see that copper is one of the main drivers, but also manganese and cobalt is a significant resource of what has economical value. But the rare earths that you have in the manganese crust or polymetallic crust seems to be quite little. But if you look at it in a relative scale and take the amount of metal used annually globally, you see that copper is approximately 2 years of global use, while other metals on this side have a relatively significant resource. So, as Ståle mentioned, the most interesting for us on seafloor massive sulfides is the copper, which is this main resource here, with also a cobalt and potential gold and silver as a byproduct when the processing is, if we're able to take that out. But on the manganese crust that you see, you have cobalt, the main driver, but also nickel, manganese, and vanadium and scandium that's used for metal alloys in several industries. That could be a very important potential. So it just showed that the resource, we have two types of resources, the seafloor massive sulfides and the polymetallic crusts. And this is our main focus, but we are looking into it and studying it further to make sure that we evaluate all opportunities. This is a picture or a map showing the spreading ridge. The system, the Knipovich Ridge, no, the Mohns Ridge going up here, and the Knipovich taking a turn up here. This is out in the deep sea. Norway started to spread apart from Greenland about 55 million years ago. Statistically, you have one hydrothermal deposit each 100 kilometers along the way of the mid-ocean spreading ridge. This ridge is 1,000 kilometers long, and science have proven that they have a lifetime span between 25 to 50,000 years. Taking that into account, we can assume that it could be more than 50,000 deposits in this area that have been overburdened by sediments, volcanics, etc. But they are available out here and should be up for exploration. So the amount of deposits and the significant resource estimate show us that we have a world-class resource to explore around. If you then take it a bit more down into what we call a play model, which are the geological concept of the discoveries, we have two types of play models for seafloor massive sulfides. You have in the middle of the spreading ridge, you have what you call axial volcanic ridges, which have the mantle plume or the volcanic plume underneath it and as a heat source for hydrothermal activity. These are located as in orange here. You see the Locust Castle is one deposit that have been discovered there, and the Aggie source is another one. These are relatively short-lived, and you have the volcanic activity covering the after they die out and split aside. So that's a lot of small deposits in the middle of the axis. But if you go to the flanks, you have Gnita Fovne deep inside here as examples, also Copper Hill up on here. These are having the heat source which generates the hydrothermal activity, which again is the source of the metal sourcing. They are longer lived, they live for a longer time, which means they get bigger. So the main potential, what we see, is along the flanks, and especially on the western flank, northwestern flank, where you have less sediment input from the Greenland side compared to the Norwegian side. And also overburden with sediments are easier to handle than volcanic overburden. So now I'll talk you through what we have identified as 4 candidates for further exploration to mining or the area for mining. As it says in the opening paper, the white paper from the authorities, the active vents are no places to no-go, and they will be are not allowed to explore around, but you can use them as laboratories to understand the spreading trends in each direction. So that's important data points to take into account. So the first one I will want to go through was actually made by University of Bergen last year. It was discovered by University of Bergen just on the northeastern flank, northwestern flank of the Mons Ridge here. Water depth just below 20,000 meters, so relatively shallow compared to what you have in the central axis, where you are down to 2,500 to 3,000 meters depth, which is have a significant impact on the production again. That when you're talking about 1/3 of the water depth. They were able to take drill cores, as you see here on the picture. They took I think they took 3 different drill cores down to 80 meters depth, and the core measurements that are on the laboratory as now show very good copper-rich intervals over several intervals. This is by far one of the largest at this time found in Norwegian waters. This is Brandstad Stadium in Bergen, and you have about 2 or 3 of these pitches, football pitches, in the size of this large deposit, but in a aerial size, we're talking about just a needle pin in the big picture. First estimates are we're talking about between 10 to 15 million tons of ore, which is a significant deposit for a license. Next one is Gnita and Fovne. This one is average values from Fovne, which is an active deposit, but it shows what average values you can expect. You have copper and cobalt as the main drivers. This one was discovered by the Norwegian Offshore Directorate, and the very positive thing about this one is that they managed to discover Gnita, which is an extinct deposit further away from it, with remote sensing, geophysics. That potential shows the conductivity in the bedrock, and they were able to locate the deposit by this type of technology. So this is also one of the good candidates we are looking at. Bones Treasure is further north on the ridge. This one is probably the most studied deposit by academia and authorities at this time. It has been drilled by Norwegian Offshore Directorate. They did the coil tube testing, or they drilled it with coil tube technology. They have used self-potential to test the anomalies, and you see you have a very good fit with the deposit and on the ancient vents you see here. So, and they have taken several courses as mentioned. As you see, this is a model we foresee how the ore body could be in the underground. You're talking about maybe 50 to 100 meters upper layers. So this is approximately 400 meters across and 400 meters down there. That's a significant deposit as well. And you see the values we have. Samples show up to 14.3% copper and 0.19% cobalt. And this one's one of the most studied, so this is very attractive for us.
Excuse me, what's the size of this? If deep inside is 10 to 15 tons, or what is sort of the most special?
I don't think you have enough data because the drill cores are very loose, so you don't have the three-dimensional point of view in that yet. But if you're talking about aerial size, you are talking about the same size and kind of the outline stretch. But on the three-dimensional, we need more three-dimensional data and to be certain on that. And then in 2021, the German scientists went up to the Knipovich Ridge and discovered Jøtul, which was the first hydrothermal vent system along the Knipovich Ridge. There you have several active vent systems. But this one, although it's an active vent system, it confirms the prospectivity along the Knipovich Ridge all the way to the north here. It's a very large active field. It has it's 200 meters across and 1 kilometer long. And the NPD, the Norwegian Offshore Directorate, went out there last year and they had a sample. This one shows, and the bulk sample of that shows up to more than 29.5% copper in that when you crushed it down and analyzed it. So this is the first discovery along the Knipovich Ridge, which confirms that you have the prospectivity along the entire Mid-Ocean Ridge within the Norwegian waters. Also, on this other side, it's important to us to make sure that the academia is part of this, and we are co-supervising several PhD programs, which we add value to our exploration. So one PhD program in the University of Southampton look at sediment cores to use that exploration as an exploration tool to identify previous hydrothermal activity. So if you take the geochemical analysis of a sediment core, you can point out in which direction ancient hydrothermal activity have been happening. The other one is understanding the alteration process of iron hydroxides, which could be used as a trap mechanism for metals, and also it could be potentially be used as an ore if it has a high copper content. So both of these are adding value to our exploration in terms of the ore and the exploration technology. As mentioned, we also look at the polymetallic crust. So we have a PhD program at the NTNU where we look at the deep sea mining system for the entire value chain on the crust as well. Just show where we have modeled up a seamount here with a 0.4% of cobalt, which would be a significant resource. If you look at the crust, there's basically the main crust zone is the one just north of the ridge on here. If you take what concentrations we have more than 12% manganese, more than 0.2% cobalt, and 0.2% nickel. If you then assume that you have a 30 centimeters thickness of this crust on the seamount, then we're talking about these numbers per kilos metal per square meters. If you compare that with a nodule field where you have around 15 kilos of nodules per square meters, you see the difference in numbers. This is a higher density metals per square meters, but it's more challenging. It could be more challenging to harvest. But this is a part of our exploration work to consider this crust as well. When it comes to technology, there's no showstoppers. It has been shown that remote sensing with self-potential, potentially electromagnetics have been used. Consortium have been out there using seismics, where they managed to show the potential three-dimensional outline of the Mons treasure here. And all of these are known technology. Been used in oil and gas for inspections. They can go down to the depth we're talking about, using AUVs from like this one, exemplified with Hugin. So there's no showstoppers in the technology that we are planning to use for the exploration. If you take the expected license work that we are now aiming to, if we get because several of the deposits, there are different degree of maturation, how much data you have available. So if you get when we get a license over, for instance, the Mons treasure, we expect to take a first cruise in 2025, where you do a detailed bathymetric mapping, you do the physical sampling, geophysics, and also you'll try to do a coring of the data based on what you have. And also, of course, you need to acquire the environmental data that you need to have to make sure you understand the mining operation. And then in the second cruise in 2026, you can go out and do extended mapping for added prospectivity around it based on the knowledge you already have acquired through the first cruise. And you need to do a detailed coring to get a perfect three-dimensional understanding of the ore and the concentration of metals. And also, of course, the environmental data that needs to be in place to understand. All of this will then go into the mine planning that will go for 1.5 years before you can do a pilot production in 2028. So to sum up the exploration, the Norwegian authorities have already de-risked the area with more than $50 million. You have several deposits confirmed, both active, inactive, and extinct, and they are all playing an important role in the exploration that's now coming. Recent discoveries show very promising copper concentrations, and we are ready to execute on the awarded acreage. And we have a world-class resource potential available for us in the first licensing round, which we are front runner on. So that was the exploration part, and I think we're now approximately halfway through the presentation. So we'll take a 5-minute break. We will reconvene at 11:45. 10:45, sorry. It's going to be a long break.
We're going. Okay, everyone. I think we're about to continue. And before we do, I just wanted to, because the issues or the various parts of the presentation, I think I forgot to mention. So we've now seen Ståle on the market backdrop and Espen on exploration. Maxime, our chief engineer, will go through production, our production system, and processing. Thereafter, Angela is going to talk about ESG, the company's perspective and a strategy for ESG. And then Ståle Monstad will come back and talk about environmental concerns. And finally, I'm going to try to wrap the whole thing up, and we're also going to look at some numbers in the end. So, Maxime, please.
Good morning. So I'm going to run you through the concept study that we are completing for the production system. Yes. So what you see here on the right is a graph coming from a study that has been performed studying the production rate of deep sea mining system in Norwegian conditions if we were to be using a system similar to what has been presented by many companies already. And what you see here is that out of all the parameters, 4 are really pivotal towards value creation, and they can be summarized in 3 points. First, you need a weather robust riser system, which basically means a riser system that you can deploy in very harsh conditions, icy states. A weather robust ship-to-ship system, which is basically the kind of operations where you have 2 ships next to one another. For example, when you're offloading ore from a mining vessel to a bulk carrier, when you're transferring personnel, and when you're performing logistics operation, maintenance parts, these sort of things. And then the last one, which is a feedback loop with the first one, is a system that lifts ore at a fast rate. If you can deploy a riser system in very harsh condition, and in addition to that, you have a vertical transportation system that can go very, very quick, then you will get a better production rate. That's the main factors. So what we have done is we have taken these 3 main points and systematically addressed them, look for what was the state of the art and how we could optimize and maybe find some breakthrough ideas. So for the weather robust riser system, the first thing that comes is that if you have a stable platform that doesn't move that much, then it's less efforts in the riser system. And that's the reason why we have selected a semi-submersible instead of a drill ship for the mining system. Because also there is a possibility to moor. And if you're moored, then you are very, very less impacted by waves. Then you can select a very rapid riser system when it comes to installation. And that's the reason why we selected a system that has bolt-free connections. These riser systems comes from the drilling industry. So they are basically joints that are made together and then lowered into the seawater column. So now we have a system that has less than 1 minute per joint compared to minutes when it is bolted. And that's a big game changer when you have hundreds of these connections to deploy a riser system. We have also selected a field-proven pipe running system that can deploy 300 meters per hour of line pipe, which basically means that altogether, now we have a system that can deploy in around 3,000 meters of water depth in 10 hours. And that's very little compared to the systems that we were looking at during the previous study, where you would need more than a day. Then a weather robust ship-to-ship system. First of all, do we need all this, or can we decrease the need for this operation? If you decrease the need for these operations, this will have a direct benefit impact on the availability of the overall system. The second question is it possible to decrease the movement between the 2 floating assets? The problem is that these 2 assets are moving independently. But if we can if we can reduce their movement relative to one another, then it will be easier to transfer something from A to B. And the last question is actually, can we just bypass the ship-to-ship challenge? First question, do we need to store the ore on the mining vessel? All the mining systems you will see, most of them, they are storing the ore on the mining vessel and then transferring on the ore carrier. And the second question is, how can we transfer personal? Can we use light craft, so a smaller ship that goes from mining vessel to the bulk carrier, where the bulk carrier would bring people from shore to the site, and then complicated with the Norwegian conditions? Is there a way to enable helicopter transfer? The issue is that the distance from the shore to the reach where these deposits are is too far for conventional helicopter transfers. And the last one is, can we reduce the amount of personnel to transfer? If we have most of the people working not on the mining vessel, but on the bulk carrier that is going naturally, doing back and forth between the site and the shore, then that will reduce the stress on the need for ship-to-ship operations. Lastly, a system that lifts ore at a fast rate. First, you need a system that can excavate at the desired rate, because you can pump as quick as you want, but if you don't mine quick enough, then there is no ore to lift, and therefore you don't produce what you want to produce. And then you need a convection system, which basically means a transport system, so through the riser, that is highly available and field proven. And that's the reason why we have looked at slurry lifting instead of with pumping system instead of airlift. A lot of people are using airlift. We have considered airlift, but our conclusion is that we want to use pumps, and I will explain why after. We have also looked at container lifting, because then if you have containers, you don't need the riser, you are more resilient when it comes to weather windows. Well, the issue is that container lifting doesn't seem to scale up. So it will work, but not to reach the production target we have. So to look at all these questions and develop our concept, we entered into a collaboration partnership with a consortium of industry players. This consortium is led by Oil State Industries, that most of you know from the oil and gas industry. They are delivering a lot of equipment to the drilling industry, but they have also delivered risers for Allseas TMC, so the Eden Gem. It's an OSI riser, and to Japanese consortiums. So the Japanese consortium that lifted SMS in Japan in 2017, that's an OSI riser. The one that has lifted the rare earth I think was last year, is also an OSI riser. OSI has been involved with all these studies, so that's also the reason why we chose them, because apart from making risers, they also have a lot of experience in designing this deep sea mining system by now. Then we also have SMD, Sol Machine Dynamics, also in the UK. They have been delivering a lot of subsea excavators, deep sea intervention systems, but they have also delivered mining machines for SMS projects. Through this partnership, OSI becomes a shareholder in Green Minerals. Before the video, I'm going to present briefly the system, the concept system. So at the bottom, you can see excavators that have been designed by SMD. Oops, sorry. Can I come back? Yes. These machines are producing a slurry on the seabed, so they are excavating ore as particles. This particle is mixed with local ambient seawater, and then is transferred to a pressure exchange chamber. This actually is not a pump. This is just a place where the slurry from the seabed is pushed upward. How does it work? The pumps are actually topside, and they are pushing seawater into the pressure exchange chamber. So that means that you have no pumps on the seabed, only an exchange chamber. The slurry doesn't stop actually on the mining vessel. The slurry goes directly to the bulk carrier. So there is no storage of ore on the semi-sub. The ore carrier, most of you may have actually noticed, this is moored. And why is it moored? Because it is connected to the mining system via a disconnectable turret, which is actually an oil and gas very well-known technology that was developed for Arctic conditions in order to be able to disconnect FPSOs for seasonal icing. On the ore carrier, the slurry is dewatered. We separate the ore solid from the seawater, and then the seawater is sent back to the riser, to the semi-submersible, pressurized by the topside pumps, goes back to the pressure exchange chamber, and then released to the environment. So that's not a closed system. That's what we call semi-closed system, because the seawater that comes from here goes back here, and the only new seawater is the top up we need to make here to replace the fraction of solids that has been removed during dewatering. Now I'm going to let you enjoy the video. All right. So as I said, I was going to come back to it. So we know that airlift has been successfully used since the 1970s, so it is not new. The first nodules were lifted with airlift in the 1970s. It has also been used in the latest pilot mining by TMC. Nevertheless, airlift comes with a challenge, several actually. The first one is it's sort of difficult to control because it's difficult to control the natural degassing of the fluid when it comes up, right? And as a consequence, you need larger sections of riser at the top in order to allow for degassing. And this comes at a cost for tension, basically, and also volume requirements. It's actually more energy consuming than pumps, estimated plus 50% of energy consumption for airlift. So that's the reason why we decided to go for pumping solutions. The current concept is based, as I said, on a pumping solution that are on top side and only a pressure chamber is at the bottom. It's actually a technology that is proven that it's used in slurry convection in land mining. It has a stronger redundancy than other setups because we can put several pumps topside that can be shut down for maintenance. Or if they shut down, then we have other pumps, and you never run on one leg, basically. The riser technology, as I explained, Oil States Industries have been delivering riser systems in the last 35 years for oil and gas, so they know what a riser is. They have delivered to the Cosmo Shoji consortium in Japan. Their riser system is on board the Chikyu for the Japanese research vessel, and they equip also the TMC vessels. It's a very fast connection system, and it has been field proven at 4,500 meters. So we are in Norway, well below that water depth. Here, pictures from the rare earth mud lifting that has been performed in Japan with this riser system. They have a global network, and they are able to deliver everywhere in the world. When it comes to the excavator, what you see here is a smaller version of our concept that has been used in a flooded pit for the Vamos project. So real copper ore in flooded conditions, and also dark. What you see on the top right is the counter-rotating heads, which are basically gathering the particles towards a central suction point. And the point of this is to minimize the fines released to the environment and to ensure proper convection into the vehicle. This is the typical semi-submersible that we considered for this study. So the good candidates are cold stack rigs, yes?
Excavator, how is that run? Is that run from the top side?
Yes.
Manually, or is it?
Yeah, it's like an ROV.
Okay.
Yeah, basically that's an ROV. Yeah, so like trenchers and these kind of things. Yeah. So it has umbilicals. The question is it has umbilical? Yes, it has umbilicals for control and power. Yes. So our candidates for rigs are cold stack rigs that are ready for sale and revamp, that are qualified for harsh environment. In terms of deck size, we were looking at something like 85 to 75 meters in footprint, available footprint. But if it's less, then we are also open to put some equipment on outer riggers to extend the available deck space. And our system needs to be moored, so the candidate needs to have mooring capabilities. Right? Right?
Yeah.
Okay. Now I'm going to go through the processing, so mineral processing. And first of all, refocusing on where the mineral processing is in the value chain and why it's important to start looking at mineral processing early in the study of a mineral project. Exploration, identify and define resources, mining engineering, convert resources into reserves. which basically mean the mineable part of a resource. And then when mining starts, the ore is transferred to a mineral processing plant where you transfer the ore into the first valuable product, concentrate. That's a sellable. It's important to look at mineral processing because mineral processing infers some cost structure information to the mining engineering, and the mining engineering will then use that in order to take the portion of the resource that has been defined by geology into reserve, what we can actually mine. It's also important to look at mineral processing because the philosophy of mineral processing may also impact the exploration strategy, and this is something I'm going to develop after that. So the paradigm here is that SMS, as Ståle mentioned, as Espen mentioned, are very, very rich kind of ore. They are actually ore that we had in 1900s. We don't have access to this rich ore anymore. We believe that they can valorize the submarginal ore and maybe what was considered as waste in existing mines. What you see here on the left is a typical ore body in an open pit. There is a portion that can be mined that has value. And then you have blue, which is suboptimal. And there is a portion that will never be mined because it's not economical to dig further with regards to the cost of expanding the pit, right? The reason is maybe because this is suboptimal as well in terms of economic value. But if you can mix super rich ore with poorer ore, then maybe this becomes a reserve as well. And then suddenly you are producing more of what exists on land. You have less waste to handle. And you may also extend the life of the mine because now you can go deeper. And that has a very important consequence on mining. It's that it can extend the life of mines. And if you extend the life of mines, two things happen. The first one is financial. You push back the mine closure capex further. So in terms of NPV, extremely beneficial. Environmentally speaking, it's also a good idea to do that because you can capitalize on the portion of virgin soil that you have sacrificed at the beginning of the mine by continuing on using tailing facilities that are there anyway. So just a small review of what is mineral processing. Mineral processing transforms the raw material ore into a concentrate that will be then further smelted and refined in order to produce, for example, copper cathodes in our case. It's very often connected to the mine site and it's very often tuned to the local ore. It represents a large capex in terms of mining projects because it includes a lot of infrastructures, and one of which is a big spot is actually the waste storage capacity or the tailing ponds. It requires a relatively constant ore feed. It's a process not like to be stopped, and is rationalized over the life of mine. And if we look at the study made by the MIT for nodule in the Pacific, the investment needed for a mineral processing plant is going to be amortized over 10 to 15 years. So then looking at this, we ask ourselves the question, can we integrate the marine super ore into the land minerals value chain? Can we boost the sub-economic ore? Can we delay mine closures? Must we invest in a new plant, or can we capitalize on the plant that already exists? Do we need to take the risk of ore delivery stoppage and basically process stoppage if we own the plant? And can we capitalize on existing infrastructures and avoid developing on virgin soils? And funnily enough, we are not the only one thinking like that. This is a very recent article where the metals company has produced their first nickel sulfate from seafloor nodules. by actually integrating in an existing nickel sulfate processing plant. So they have not invested in a new processing plant. They have reused an existing plant. If we look at SMS in isolation of the existing ore, because of their geology, there is almost no overburden, so there is no waste to remove on top. Because of their ore grade, then we can look at waste reduction up to 75%. When I mean waste, I mean rock that has not enough value in it, that will never go into the processing plant. And tailings reduction up to 50%. Tailings is the waste coming outside of the processing plant. So the non-valuable part of ore that has been depressed after, for example, flotation. As a bonus for land, SMS waste can be separated on the seabed. Then we don't need to use some land space to handle and store them. They don't provoke, they don't arise a risk to land water source. One of the main issue with storing sulfidic waste is that they are sulfidic. So if fresh water touch it, start producing sulfuric acid, and then it's called acid mine drainage. You might have seen these pictures in Brazil, for example. You have these kind of orange rivers. That's basically a waste pond that's been raining on it, and this went down the hill into the river. Here, if we segregate them on the seabed, we obviously are never in contact with fresh water. And seawater can act as a buffer. It's not the same as fresh water. It doesn't have the same ionic properties. So it is less actually production of acid, if acid at all. So in order to prove or go ahead with our hypothesis that we can integrate the marine ore into the land ore value chain, we need to look at the blendability. Can they actually be mixed? Are they genetically compatible for being put together in the same processing plant? As I said, building a new processing plant means high capex. And if we look at high capex, long life of mine, it has a direct impact on the amount of resource you need to find during exploration stage before you can actually click on investment production. On the right, with our hypothesis of 1.5 million tons per year, if we need to go MIT hypothesis 10 to 15 years of production, then we need to secure 22.5 million tons of ore in our exploration portfolio before we press the button of investment production. But if we can integrate into an existing facilities, then the only requirement comes from the long-term charter for the deep sea mining operation, the production system. With our hypothesis of 5 years of long-term charter, that means we need to secure only 7.5 million tons of ore before we can take the decision of starting production. So we knew from before that they are genetically related, because on land, the VMS or baby or SMS or babies VMS, after millions of years, they will end up on the land. But a lot of things happen during this moving, so we had to verify that they were actually compatible. So we acquired some typical copper ore from land, and we acquired some SMS ore from the Mid-Atlantic Ridge via our academic partners in the UK. We took samples that were actually not that rich in ore. And actually, they are blendable. We tested 15 different setups, varying the ratio of land ore, subsea ore. We have only used common reagents for flotation and depression. So what is used commonly in the land processing value chain. Same comminution. So comminution is the crushing you need to do in order to transform the ore into a powder before it goes into the flotation cells. And they can be floated together. So using the same kind of reagents, so there is no showstopper to actually put this marine ore into the land value chain. And as such, our business plan for smaller reserves requirement stands.
Good morning. Green Minerals is very committed to responsible business practices. Since its first year, we've been building our ESG framework, and we have, without regulatory mandates, we have been improving and updating our work. To make sure that this all consider in everything that you've seen today, presented today, our chief engineer is directly involved in the development of the ESG framework. And our purpose is to understand, strategize, and anticipate all risks and opportunities that we can on environmental and societal footprint. Green Minerals is also a participant of the UN Global Compact, and we support the Sustainable Development Goals. With our experience from all this process and guided by international instruments like OECD and the UN guidelines, we are shaping our governance structure with focus on environmental impact protection and mitigation of impacts. We consider three essential tools for this, and where we count on the stakeholder engagement to integrate their perspectives in our decision-making process. We also, very relevant, our due diligence process, where we ensure very thorough assessment of potential risks, enabling us to make responsible choices. And a reporting process where we not only benchmark our performance against industry standards, but we also facilitate comparability with other companies and track our progress over time. Green Minerals proudly produced the first sustainability report for the deep sea mining, now on its third edition, updated edition, and in accordance with the Global Reporting Initiative. And why have we chosen the GRI? GRI is the most widely adopted framework globally, with 73% of the world's largest companies adhering to its principles. And also they have introduced standards tailored to the mining sector, which reinforce their relevance to our work. As do our current activities, to set KPIs and targets can be challenging. But our reporting process enabled us to identify material topics that are important to our stakeholders, especially the environmental impact. And with the feedback from our stakeholders and our technical team, we can translate these concerns into strategies for environmental protection. Also, besides our internal initiatives, we contribute to industry-wide progress. And one of these endeavors was the collaboration for the development of the Handbook for Marine Minerals that aims to establish guidelines to facilitate comparability and tracking of progress across the industry. This project exemplifies our commitment to collaborate beyond our work inside the company. As mentioned, now we are reporting in accordance with GRI, and we also produce annual communication on progress for the UN Global Compact. And for the first year, we're gonna produce also to comply with the Norwegian Transparency Act, where we report on the due diligence on human rights. Looking ahead to 2025, and with the commencement of our exploration activities, we are planning to adopt the ESRS and the TCFD. And furthermore, we want to raise the bar and take more meaningful commitments and start with the science-based target, for example, to keep driving our journey to sustainability ahead. Thank you. Now,
Thank you very much, Angela. The environmental concern is, of course, has been sort of the greatest source of controversy around this industry, and it is something we take very seriously in Green Minerals. And today I'm just going to try to explain our view a little bit and why we think this is one of the absolutely most the best way for nature to get the metals we need, because there has been a lot of writings in papers and magazines. Some are positive, a lot of them are negative, but we truly believe that deep sea minerals needs to be accepted as an enabler for the green shift. I was touching into this topic a little bit on the backdrop. We need to accept that we have to extract new minerals from somewhere. And we also need to accept that every action, particular extraction, mining in itself, has an impact on the environment and on nature. That is unavoidable. So the question is more, where can you get a kilo of copper or a kilo of cobalt, whatever it is, for the least amount of environmental impact, negative impact. So, because the impact is going to be there, no matter what you do as humans, everything we build, everything we do has an impact on nature. And one of the things we're faced with is the perception that is out there. Every time it's written in one of these articles and papers and so on, the images they choose are very colorful. It's full of life. While if you take a look at the videos that the NPD have put out, I think there are, how many hours you have? 3-4 hours of video going along the seabed. This is more what it looks like. It's never a photo like this in the paper. It's always like this, or with sometimes they use the images from 50 meters of water depth with crabs and fishes and everything. So it is creating a perception or sort of a mindset in everyone who doesn't really have an insight into the industry. I think there are several sort of types of impact. One is the indirect environmental impact, which is the energy consumption. We know that energy is a resource that is we don't have enough at the moment, or we have enough, but it's under pressure. So how much energy do you actually use to produce the metals we need? And to take something from a rock into a metal uses a lot of energy. Really, one of the main energy consumptions in the world. So if you look at this red line here, it's up there. That is a typical Nordic mine from Finland. In Sweden is even lower. So we are around 40 gigajoule energy consumption per ton. If you look at the star of the copper world, which is Chile, we are just below 30 gigajoule per ton of copper. And if you look at the spread between 2 and 6% that we expect for SMS, we are less than half of that energy consumption just by the processing of the ore. So that is a positive indirect environmental it's a positive. We use only half the energy compared to what you use on land. And then you have the more direct environmental risks. And I want again to emphasize a bit, what kind of assumptions are we putting into sort of the narrative? Because all the images that you see, which are particularly from institutions against deep sea mining, you have these kind of drawings. You have a huge collector plume here. You have a dewatering plume. You have a lot of noise all the way down along the riser system. Well, no company in Norway plans to do anything like this. It is not what we are planning for. Like Maxime explained, we're going to take all the water all the way back down to the seafloor. We don't have any sort of noise or pumps along the riser that disturbs the communication of waves or whatever it is. It is just not reality. It is something that is an assumption that is wrong, and that's the way it is. So the main risks has been pointed out is sediment plumes, is noise, is light pollution. We're not going to use any light. This is robots working. It's not humans. Toxic waste, and for SMS, destruction of the endemic ecosystems around the black smokers, because they are unique. They are something very special. The environment that lives around these active smokers, because they live on the energy from the heat that comes out and from the methane, and they live on the sulfur and so on. Once these hydrothermal events die out, which they do after between 10 and 50,000 years, something like this, or the endemic ecosystem dies with it, because they don't have the source of food to survive. That's one thing. The other thing is there's no one who's going to go anywhere near these active systems, because they are environmentally important. That's one thing. They're super hot. It's like we talk about 300 to 400 degrees close to the surface, and they're very acidic. And the water around it is super acidic, and it's full of metal ions and everything. So it's not possible from a technical point of view, and it's not desirable from an environmental point of view. So you can just put a big red cross over that. No one is going to mine any black smokers. When it comes to sediment plumes, I will come back to it a little bit later. The noise, like I said, the noise is not a big problem along the riser, because we don't have any pumps. And when it comes to toxic waste, what is the sort of the concern is actually metal ions into the water. Well, the water in these areas along the spreading ridge, in the mid-ocean spreading ridge, are really full of metals. That is why we have the deposits out there. All these vents are spewing out enormous amount of metal ions. So even if there are some grains coming out of the mining, it's very little compared to what's there naturally already. And this is a very active system. It is a lot of faulting. There's a lot of sliding, rock slides. It's volcanic eruptions. It is already a very challenging environment to live in, to put it mildly. So this is a hypothesis about the plumes, like it's very often published in papers and so on. This is from Dreisen et al. In Hawaii in 2020. And then we have the reality. Because this has been monitored actually by MIT in Boston, by DHI in Denmark, during actual sort of test mining operations. So what they observe is that almost all the sediments that are mobilized stay really close to the seafloor. It doesn't rise up through the water column. Not like it's drawn here, that it rises for, I don't know, 2,000 meters or whatever they have it here. It stays very close to seafloor, and it doesn't spread a long way out away from the mining site itself, which is two very important things. When it comes to the mid-water plume here, that is if you release the return water in sort of in the middle of the water column, which we are not going to do. We're going to bring it all the way back down to the seafloor. And this is a video from a test mining in the Pacific. And again, I just want to stress this is nodules. It is a very soft bottom. It's full of sediment, so it's more plume here than we expect from SMS. But we don't have a video from SMS, so I'm going to use this one. And this vehicle here is actually the collector. So what it did, it has a camera on top, and it did the mining, and it turned and went back into the plume. Because there is plume generation in this run. So now it's going into the plume, and as you can see, the camera, which is 3 or 4 meters above sea level, stays actually on top over the plume for almost all the entire drive back. So the plume rises, even in this very sediment-rich area, rises only 5-6 meters above sea level, and then it settles back again. And that's in accordance with all the modeling that MIT did and DHI as well. And we realized that we have to do similar modeling along the mid-ocean ridge we have in Norwegian waters. And then I want to I'm going to try to visualize the aerial effect, because one thing is sort of the effects that might spread out from the mining site to other areas through plumes or noise or whatever. But the other thing is, what is the direct sort of the hole we make and the impact? How big is it? So I'm going to use an example from Utah, which is a big mining state in the US, and compare a little bit with the mining that we are looking into in Norway. If you look at the scale, this is a scale photo. So this is the scale of the entire state of Utah. And this is the original assessment area in Norway. The distance here is 1,500 kilometers roughly. Here it's 500. So it's a much larger area compared to Utah. And in Utah, one of the biggest mines is the Butterfield Canyon, Bingham Canyon mining area. And as we can see in this one, if you can read that far, it is actually 65 kilometers across, while an example of the Loki Castle from tip to tip is 120 meters. So it's a completely different scale. It's really condensed deposit, the SMS, compared to the size of the onshore mine. And remember again, we need to take these metals from somewhere. We need to dig a hole somewhere. It is not available to us, and we need it. So if you take that typical Loki's Castle and put it into the mine, this little blue dot here, that is a representation of one sort of operation, deep sea mining or SMS operation. It's going to be this size, but maybe a little bit larger, but not much. And again, if you take the Bingham mine into Utah, it is, oops, go back. It's supposed to be a little circle here. It's between these two green lines. It makes up a very small part of Utah. So my point is really, even though the area that is outside Norway is very large, and it's been sort of, again, the narrative in the papers is like, we're gonna mine an area larger than Germany or larger than, I don't know which country they compare to. That is the exploration or assessment area. The actual mining is going to be very limited. And when we are done with one mining site, we can lift all the equipment, sail to the next one, and lower it down again and continue. There's no infrastructure left on the seabed. It is really like surgical interventions when you compare it to a large area. So just for this audience, to compare it with Nordmarka, if you scale that area to Nordmarka, having one of these operations out in the deep sea is equivalent to one of us walking into the Nordmarka area and digging a hole of 20 centimeters. Or maybe we are looking at 10, 20 of these sort of excavations in Norwegian waters, 20 centimeters hole in the Nordmarka. It is a very small area that is directly impacted. And we, like Maxime explained, we have designed in the concept study a system that is minimizing all the environmental effects or impacts, negative impacts. We are bringing all the return water back down to the seafloor. We don't have any pumps along the line disturbing any communication channels, anything for mammals that might use that. We have a system of counter-rotating excavation heads that goes into the middle, and everything is sucked up, so minimizing the plume. From all the studies we've seen, the plume stays very close to the seafloor. It doesn't move around. So it is important at least to have the right parameters in your head when you evaluate if this is a good idea or not. It's not very good to use the wrong assumptions. Right. I hand it back to you, Ståle.
Okay. Thank you very much. So going to try to wrap it up here and look at some metrics and some numbers for the investment case. And but before I do, I'd like the Nordmarka analogy, where I think nobody would claim that if you put the shovel down in Nordmarka and dig up one of them, that you would ruin Nordmarka. And that is probably the same thing that Norwegian politicians have understood when opening up for deep sea mining in Norway. It's really surgical intervention into a very, very large area. All right. So how does this look then from an investment perspective? First of all, what strikes you when you look at the numbers for deep sea mining, for what we are going to do, versus traditional terrestrial mining, is that the economic metrics or the economics of this is such that we could talk about a disruption in terms of comparing it to the economics then of traditional mining. As has been said several times here today, there are no infrastructure investments needed in deep sea mining. Now, if you want to open a mine, a terrestrial mine today, you need to go to faraway places, often into the rainforest or the like, and you need to build substantial infrastructure, a substantial interference, even before you start mining. And this costs billions of dollars, and it takes a lot of time to invest and to create this infrastructure. In deep sea mining, we don't have that. We just take a ship and go where we want to take this up and start producing. The capex per ton of copper, and this is mainly a copper play, as we have shown today. The capex per ton of copper produced is $17,000, and this is to be compared to capex per ton of copper produced of $30,000 for onshore mining. So there already we have an additional significant capital advantage in deep sea mining. Also, as shown here today, there is zero sunk cost in the mine. That is, we pick up the equipment and we leave for the next site when done with the deposit that we're producing from. As Espen showed there today, there are various sizes of these deposits, ranging from a few million tons to maybe up to as much as 10 to 15 million tons. And with the production rate of 1.5 million tons, the mathematics is such then that we stay in one place for 2 to 3 years and then move on. And as Espen showed, it could be up to 10 years production from one site. Furthermore, and this is super important, the business model that we are looking at is an offshore oil and gas services business model. That means we are looking to rent the equipment. Just like if you're an oil and gas company, you rent a drilling rig from a contractor. We are looking to rent a drilling rig from a contractor. And then we have a consortium that provides the subsea equipment. This is different from the traditional mining model where everything from the billions of dollars in infrastructure investment to the equipment goes on the balance sheet of the mining company. We don't do that. This is super important when you look at return on investment for within deep sea mining. So asset-light business model, very high capital efficiency, very high return numbers, because what we step into is the cost structure of the traditional miners, and the price levels set in world markets are of course dependent on this cost structure. And the disruption happens when you put a very different business model into that market. We get the advantage of a very high copper price based on very, very high cost. We have low cost ourselves. When it comes to environmental, as Ståle showed, there is, as we see it, having worked with this for some years now, there is a difference here between perception and reality. There is a study done by Polikas et al. 2020, this is for nodules, that points to on a number of factors, including environment, biodiversity, and so on, points to a 90% reduction in the environmental footprint in deep sea mining versus terrestrial mining. And I think we have shown here today the reasons why this is so. We will operate a semi-closed loop harsh environment deep sea mining system. There will be no mid-water plume. Return water will be transported to the seafloor. There are no pumps along the riser that creates noise. And as Maxime showed, a sharply reduced overburden leads to less waste and less tailings, which is important. I can add, I don't know if the listeners are aware of that, but there are around 3,500 tailings dams worldwide. More than 800 of these are in Brazil, as the Western world prefers to have this industry onshore, which creates a lot of waste. It looks like the Western world prefers to have it happening in developing countries rather than in our own backyard. 3,500 tailings dams. The expected number of breaks on these tailings dams is 3 to 5 every year. Think about that number. 3 to 5 of these dams are expected to break every year. Every one of these that breaks is a disaster. It's a natural disaster where it happens. And there's been a few of those over the years, amongst others in Brazil in 2016. So to help reduce that pressure on those areas is something that we are proud of. Key metrics on the investment case. So Green Minerals is a copper play, first and foremost. We are targeting a world-class copper resource. This is happening at the time when the copper market is about to enter deficit, as Monstad showed. It's an extremely good timing for this. To have a new terrestrial copper project, to bring that on stream takes 10 to 15 years. 10 to 15 years. And the market is about to enter deficit now. So in that sense, our project also has an advantage of being able to be brought to the market at an early stage compared to everything that you see onshore. We mentioned this before, but I want to repeat it. I think it's important. Despite the modest market cap of the company, $50 million of exploration data has been transferred to us at zero cost. And I think Espen showed clearly what this data is doing for us in terms of understanding the geology there. The company expects a license within the next few months. If you take one Green Minerals harsh environment deep sea mining system, we are looking at the production of 1.5 million tons per hour, a 5% average copper ore grade. That gives us an expected annual EBITDA of $176 million. And this is company EBITDA, not project EBITDA. The project EBITDA is far higher. And the reason is that we pay the contractor, we pay the drilling company or the rig owner to do this work. So project EBITDA is substantially higher than this. This company, just to put a number on it, this company will be able to pay the drilling contractor a day rate that is, if you compare to high-end leading day rates today, around $500,000, we are looking at a number that is 70% or more higher than that day rate. So we think we have attractive business to bring to these players. We're very excited about the discussions we're going to have. Max drawdown on cash is $50 million. I will show you how this looks in terms of timeline. And the payback time for the investment on the company level, not on a project level, is 4 months pre-tax. And I'm saying pre-tax because the tax system around this has not been decided on yet. We think it will be a normal corporate tax rate, but that remains to be seen. So in order to talk about numbers that we know and not speculate on it, we talk about pre-tax. And that gives us a cash return on investment on the company basis again, or more than 300% per annum, pre-tax. This is how the cash flow profile of the company looks. And again, just repeat what I started off saying is that when we started this company, our ambition and our goal and what we told our investors that we would work extremely hard to deliver was a world-class copper resource with a minimum use of capital. So far, we have delivered all that. The company has a burn rate of 2.5 million Norwegian kroner per quarter. If you compare that to the other listed company in the world, the metals company, they have a burn rate of $15 million per quarter. And this is all back to this asset-light thinking, this partnership thinking. We have met, we have, of course, talked to senior people at TMC, and it's just a whole different thinking in terms of how you approach this resource and what you need at any point of time in order to drive the process towards license. And so far, this has worked extremely well for us and has been beneficial for our shareholders. Getting access to this license with a minimum use of capital. When we start exploration or the sorry, I think I went back there. So when we start our exploration or the add-on exploration, in addition to the data that we have, and the environmental monitoring and so on, we will start to spend some more capital. In the area, we think of around $10 million per year. Still, at the maximum drawdown point for this company, which is 2028 when we start producing, we will be below $50 million spent. What you get in return for the $50 million spent in total on the company level is a cash EBITDA coming back of $176 million based on today's copper prices. And we already talked about the copper market entering deficit. We've seen BlackRock, Goldman Sachs, and others talking about higher prices, 20% up in order to necessary then to invest in new projects terrestrially. And others have forecasts of far higher copper prices. But only on today's price, $176 million against this cash drawdown. And then, as we can see, the cash builds extremely rapidly in the company into the hundreds of millions of dollars quite soon after we start production. So in summary then, just want to start with actually the bottom statement there. Green Minerals is primarily a copper play. We as a company has spent a lot of time deciding on which resource we think is the most attractive. And this has been really important for our strategy here and our thinking that Norway and the SMS deposits is really the most interesting deep sea mining play to be had. We also have an MOU on a license in the Clarion-Clipperton Zone, and this is a really, really big license. To put some numbers on it, there's more than 200 million tons of wet nodules, $40 million has been sunk into exploration on that license, and the size of the license is humongous. It's equivalent of 180 North Sea blocks in oil and gas. Or to put that in perspective in terms of listed Norwegian companies, this is the MOU that we have there on, or the license that we have the MOU on, is 5 Aker BPs in terms of size. It's truly big. The International Seabed Authority has said that they will deliver the mining code by July 2025. And we are very happy with that in terms of our own timeline in Norway, meaning it gives us the time to work on this MOU and to get the best result possible before we start the transfer of rights to Green Minerals. But as you understand from what I'm saying now, is that when we look at the qualities, the minerals that are represented on the CCZ, we are more bullish, we are more confident on the SMS deposits than we are on the nodules. I can, for example, say that the first player that starts production of these nodules is going to have a really big impact on the manganese market. You're not going to see that in copper. We are not going to impact the copper market by producing. But the first one who starts producing nodules is going to have an impact on some of these much smaller markets that the nodules go for. So I just want to make a point out of that. Otherwise, we have been delivering on our strategy and fully intend to continue to do so, and we're ready for the next step. The Norway 9th of January decision is massive for the company, de-risks the business case, and we have now been invited to nominate acreage for licenses. We believe Green Minerals is in pole position to win licenses as soon as the first half of 2025. The production concept Maxime has shown has been developed together with globally leading partners and is ready. And all the elements that you saw on what Maxime presented is basically TRL 9. These are known technologies put together in our own way and with a good bit of input from Maxime himself. We have proven blendability SMS with onshore VMS. This is super important for the business case, and it adds industrial value. And it is hard to imagine that any onshore copper miner in our vicinity would not be interested in ore that is 20 times richer on copper than what they produce today. That is what we're talking about. Mining infrastructure in Nordics is well developed, and you saw where we plan to ship the ore. Our current plans, it's Narvik, and the infrastructure is in place. The DSM metrics, as I said, is superior to traditional terrestrial mining. Importantly, it allows us to produce copper with a different business model, super important. It impacts the economics in the case substantially, and not least on ESG factors. We talked about environment today, but we could talk about other things, such as social, such as cobalt production, for example, in other places of the world. But just to stay with the environment, there is a reality that we see down there from the work we're doing versus the drawings done on land by people who's not been at the 3,000 meters looking at what's there. We have an unusually strong investment case financially. Stated annual EBITDA, pre-tax cash return on investment of 300% per annum on company level, and the pre-tax cash payback of almost unheard of 4 months. And the market cap on all of this is a modest $8 million. So with that, I think we have concluded the prepared presentation. We have stayed within our timeline, actually beating it by 4 minutes in Green Minerals style. So happy about that. And we are open for questions. We welcome questions. And also we are going to hang around here for those who might not want to ask them in public or rather have private conversations. So please, anyone?
Maybe one from me, Ståle. How large is the variance in terms of ore grade? I think you showed one example at Moonscot, and it was 14.3 in the example in the economic calculation 5. How much brines can we see there, maybe in one deposit or overall?
I think I'll leave it to the geologist to answer that.
It is a difficult question to answer because we don't have all that many data points, hard data with coarse samples. What we can do is to look at how does it look on land, like I think it was Aspen said that, or Massimo said it. But these SMSs eventually ends up on land maybe in 100, 200 years time, but it's the same. This is the process that created all the copper that was taken out of the rails and left in on these mines in Norway. So we got a fair idea, but there will be differences in different zones because what sort of controls the precipitation of copper is temperature and pressure. So that could vary a long time, and suddenly you just put a zinc here, and then it increases the pressure, for instance, and then copper comes out or decreases. I mean, so it is. But we see that the example that Aspen showed of 29.5% copper in one rock that they took from Jøtul is extreme. And then you have other samples with 0.1% copper from the Nitahaug and Moose pressure samples that is really low. So that's the span that you have. But we believe there are zones that are rich in copper and others that are not rich. And one of the beauties of this type of mining is that you don't invest in roads and build facilities on the place. If you reach poor areas, you can just lift up and go to the next one. So that is the idea. That's why we use relatively high average ore grade of 5% in our economics, because we do not want to mine bad rocks or lower grade rocks. We want to focus on high grade zones. Sometimes that is easier to do than other times, but at least much easier when you do marine type of mining compared to that, because you don't have any sunk cost. I mean, if you invested in a road and a plant, you need to dig until you are broke.
Okay. Anybody else in the room?
Yeah, I have a question. Or a couple of them. You talked a bit about plumes. I was wondering if you've done any modeling in the Norwegian Sea, or is all the results that you referred to from the Pacific? That's one question.
Yeah, okay, let's take another one.
Yeah, and then you mentioned that several of the interesting points are active vent fields, which you also mentioned that you don't want to mine on. So I'm just wondering how you will differentiate between them, particularly as the scientific knowledge is a bit uncertain on how you can determine whether a field or vent is inactive or just sleeping. And there are examples of vents being activated by mining operations for sampling of inactive vents.
I'm not aware of that. So your first question was the plumes. All the examples and all the studies that are shown are from the Pacific. That is where it has been been going on for the longest time. The exploration has gone on there for 20 years with different companies. We do work with another company, and we're setting up a system also for Norwegian waters. One thing that has been done is a mapping of the sediment layers. Now I'm getting a little bit geological, I apologize. But the sediment cover inside the rift itself. And that is done by a guy called Stutzhagen at the University of Bergen. They looked at the very shallow seismic. And then you can see from these images that it's a very thin layer of sediment, but it's evenly thick all over the place, meaning that there are not many currents moving around. If you go to Oslofjorden, if you have a rock sticking up or some high, it will be no sediment at all on top of that because of the current washes away the sediment and it deposits it in the loess. That is basic sedimentology. What we see out there is that it's just even sediment layer, very thin but even, indicating that there are very little strong currents able to move sediments. So that is an indication. It's an indirect sort of pointer towards not much transport of plumes are possible because of this. But we are asking, you can elaborate if you like, but we have started a cooperation with the Danish Hydrological Institute, looking at plumes specifically for the mid-ocean ridge in Norway. And I think, do you have anything else to add, Aspen?
No, that's one of the first things to understand the local variation in plume, and as Joel mentioned, there's very little sediment variation, which then indicates that there's continuation of sediments coming into the system. But of course, to understand the local variation in plume, it's important.
And then the second question, you have to remind me.
So it's about how you will determine whether
right, the active, yeah.
Inactive or sleeping, and also perhaps if you could elaborate on the data that people gathered before actually sampling the estimates to have a reference.
Well, when it comes to the requirements, we have discussed this with the Energy Department and with the Offshore Directorate, and I think most of the very small community of deep sea mining companies in Norway agree that it is a good idea that the authorities come up with specific requirements for environmental data collection and observations before we actually do anything, because that makes it a bit more easier to know what you're going to do, what you are not going to, what's not important, what is important. But then, with the help of environmental department and so on, put up a set of criteria. This is what you need to have a handle on before you can start. When it comes to the active or you call them sleeping, sometimes there is a little bit of activity, typically like 20 degrees of water coming out and not 300-400 degrees of water coming out, so still a little bit of life going up. I'm not aware of any cases where mining has waking up a sleeping vent. I don't know where you have that information, but you're welcome to send the publication if you have it. And avoiding these is not difficult in the active one because they are black smokers. It is really the easy thing to see down there. Both from you can use chemical sniffers, you can use optical instruments. You will see the black smoke coming up, and we need to avoid that both from an environmental and from a technical mechanical point of view. And lastly, we think that like Aspen said, the most interesting part is the flanks, where you don't have this, it's not as dramatic as you have in the actual valley. You don't have the same sort of, it's a little bit cooler system. It doesn't have the same temperature because it's a long way to go from the magma up to where they actually precipitate the metals. So of course we're going to stay away from all the active vents and the venting. Yeah, I don't know what else I can say. We're going to stay away from them and distinguish between an active and an inactive or extinct disease.
Okay, should we take some questions from the listeners here? One is, could you advise on the exploration, the depth and the overburden that you're anticipating? I think we talked about it throughout the presentation, but is there anything to add over and above what we had?
We're working with depths. As one deposit show, we are around 1,000 meters and down in the actual valley,
1,000 to 3,000.
1,000 to 3,000, and the overburden we're talking about on sediments is well, not very much. We're talking.
Most of them are actually outcropping, so there is no overburden.
There's only a marginal outcropping, and that is one of the pillars of the strong environmental case we feel for the resource. And then we have one here for the deep sea mining process and the invasive gathering extraction on the crust vents by, I assume, some kind of AUV. Is there going to be AI assessment by the use of machine vision on the fly, or interfacing the flora on the targeted extraction points? I don't know if anyone wants to have a go at that.
Well, AUVs are not going to be used for any extraction.
For production.
It's an observation and data gathering tool, the AUVs. But there have been some proposals from some companies to use AI assessment to avoid environmental biological life during nodule picking. It's not so relevant for SMS.
Yeah. Okay, and then we can go to, for example, this one, I think is interesting.
Yeah. There is a lot of questions from Mr. Luke Brown.
Yeah, we are not going to answer every question from Luke Brown,
actually,
but SMD's Sovara work on production vehicles lasted around 10 years. How does this compare to our timeline?
I think they're all from me anyway. So first one, 10 years, yes, because they were the first one to be produced. So you had all the design phase to do, the tasting phase, and then, okay. Now what we are going to do is take all this experience that is already being gathered, has been already designed. So our lead time for the full system is 3 years, mainly driven by the waiting time in naval yards.
Yep.
So nothing to do with the robots, actually. Are you planning to recover any other metals besides copper? Yeah, actually cobalt. Part of the mineral processing study was to identify where the cobalt was located in the mineralogy. The cobalt is intrinsically in the pyrite. So if you want to recover the cobalt, in addition, you have to do the retreatment of the tailings, which is another study that we're planning on.
And I think we just go to yes, you already
very briefly. So Nautilus Solvar 1 project is a mobile system by definition because it's a different geology. The SMS of Solvar 1 were on a fast spreading ridge, so it's almost a 2D deposit. It's not much expression in depth. It was very, very wide, actually. Yeah. So very different. Our system is more fixed because we are looking at different geology.
Yeah. Can also just add that there are big differences in terms of how we approach this resource and approach the whole project from a business case point of view, which we have explained with the numbers as well. And then this last one, Maxime, have you identified ship-based or seafloor drills that will be essential for resource definition?
Let's see. I can.
Oh, yeah.
I-
Well,
yeah.
no, go ahead, Ståle.
No, I can take that. Yes, we have, there are at least 2 systems that we know of, seafloor drills that can be used. We are not anticipating using ship-based drilling in our exploration.
Okay, we can take next, although the first pass exploration has been provided by the oil directorate. What are your plans for detailed geophysics and drilling to define alteration in your deposits, and when will that kick in?
Well, the first pass exploration or the next pass will be after license award and first cruise in 25. So then you need to do a detailed geophysics of the deposit that you find most interesting to get as good as it gets a 3-dimensional overview of the concentration and the ore itself. Based on that, then you need to do drilling. The first drilling, which again will lead us to the second cruise, which again we have to take to get even better drilling, to get or even better 3-dimensional overview of the ore. Yeah, so that's the general first exploration plan.
Yeah. And here's a question on the whole licensing process and approval process. So, Ståle, do you want to have a go at it? What type of companies do you expect to apply for Norwegian licenses? Mining companies, trading companies, what is the expected competition, and also the timeline?
Yes, it's a question in 2 parts there. The first one is ISA approvals. It's not really what we focus on the moment. We will follow closely what happens at the ISA regarding the MOU we have for the license down there, but it's not relevant for Norwegian license. So the type of companies we expect to apply in Norway is actually deep sea mining companies or companies that have already flagged themselves as interested, and it's quite a well-known cluster of companies, not too many. So the competition is there's more than enough acreage in this first round for companies that have done the work beforehand, like we have.
Yeah, and I think just to make that clear, so Norway has sovereignty over this area, over the Norwegian continental shelf, and has how should we say, large degree of self-confidence in its ability to manage natural resources after having successfully done so with oil and gas, also offshore over the last 50 years. So Norway is driving this process from a domestic perspective. All right, last one.
I have a question. If that's okay?
Yep.
Yeah. The resource estimate that was kind of put forward as part of the opening process has been heavily criticized for being misleading and blown up and kind of too big from, among others, the Norwegian Geological Survey, and they are proposing a copper estimation of 1.5% instead of 5%, as you're talking about here. And you, they're saying that the earlier estimation from SODIR, were based on too few and shallow samples. So do you disagree with NGU on this, or do you have documentation that kind of counter NGU, which is the main knowledge base here?
NGU is the main institution for onshore geology, that's correct. And I've discussed this only, I think, 3 weeks ago with the author of that report from NGU. And I'll try to give a brief explanation. Again, they have compared onshore copper mines in Norway and in the area around and see, well, what is the average grade in here? But the average ore grade for a mine is dependent on how far out you're willing to go with the mine. If you construct a row a processing plant and like a small town almost around an area, and you start mining. And maybe you start with the best parts, and then you have to do more mining because you already have the plant, so you can just as well do the mining. So my point is, the average ore grade of that mine is dependent on when is the commercial sort of economic cutoff value for mine. Like I said in the beginning, in Sweden, they are now the biggest mine in Sweden are now mining at 0.17% copper. In Finland, Kevitsa mine, the Rusal mine, they are around 0.2, 0.3, something like this, because they already have all the stuff built, so they need to make the most of it. So when you say what is the average ore grade on this mine, it would be, of course, drawn on quite significantly, but delayed the production. When you go offshore and do mining, like I said, you know when a mine when it's not commercial, so you don't have any sunk cost. You just lift it and go to the next one. So it is a completely different sort of setting and sort of circumstances around it. So it's not wrong what Andrew put in there. That I think they're close to 2% instead of 4%, but it's based on maybe 1.5, based on mining averages onshore, which is a different situation than mining offshore.
Yeah.
So I don't know if you understood what I meant.
Right. So in conclusion, if you want to talk about minerals in the deep sea, you should probably talk to a deep sea miner rather than an onshore miner or onshore geologist. All right. I think we are sort of approaching the end of this. No further questions coming in on the screen. And so we want to thank you all for participating, and especially those who came here in person. We appreciate that after these hard years that we just have come out of. So thank you very much. And again, we'll be hanging around here. So any other questions here physically, we'll be happy to discuss them.
Thank you.